All right, welcome back. Today is November the 4th, and we're going to continue here talking about chapter 9. And so, this part of the book in my previous version was chapter 10. So, that's why I call it now chapter 9b, because the book split the substitution from the eliminations. And I kind of like it that way better than the way it's now, but version 8 blended everything. So version 8, chapter 9 includes both. Then your chapter 10 will be alcohols, and that will be the chapter 11 that you will see on the first slide on the recording, but don't pay attention to that because the link will be same as chapter 10. So it will not be a confusion on that in that sense. All right. So let me tell you some very important concepts here on elimination. And so once we finish this, then we can go to the practice homework, which I have ready here for you guys. Where is it? Right here. All right. Just bear with me one more time. And so here is the elimination. So in the elimination reaction.
Dr. Odens, we can't see your screen.
Oh, thank you very much. All right. So where are you? Oh, right here. I thought I hit share screen. Oh, who's this? Oh, okay. Got it. All right. Can you see it now? You see me? Don't see me? All right.
Yes, we can see it now.
All right. Thank you, Nima. Okay. So I'm gonna remove this because I'm tired of talking through this thing. I think we're far away. Remember how I started this class with the shield? my glasses were all foggy. I had the mask on and I removed the shield. Now I'm removing the mask. That's all I'm gonna remove. I promise. That's as far as I will go. Oh, maybe my glasses. The glasses too. Yeah. All right. So elimination reactions. Now I feel like I can talk. All right. So in the elimination reaction, you want to withdraw the hydrogen that is 180 degrees from the leaving group in the carbon that is next to it, like it's shown here. This hydrogen in blue, we're going to remove it with a base. All right. That elimination is known to, hold on a second, I have a little loose cable. It's known as an anti-periplanar elimination. So anti-periplanar means that the hydrogen that is being taken will be 180 degrees on the plane. So the plane is this bond here that connects the two carbons, and so that's called peripheral. The peripheral, the H and the leaving group are in the peripheral like that, and so it's anti because the H that is taken is in the opposite side of the leaving group, so it's anti-periplanar. All right, so that's what it's called. And it's also an elimination. So all the elimination reactions will give you an alkene. All right, that's what you're up against. So notice that if you had like chiral groups like here and here, when you were going to do this elimination, the base will grab the H and these two electrons are transferred there and the leaving group leaves, just like I have it in here. So the base comes, grabs the H, makes the double bond there, and it kicks out the leaving group. So if I have different groups, this will be a CH3 group here. My ethyl group will be there. Because notice that this CH3 and this phenyl will be on my side, and here will be that CH3 group here. So the CH3 and the ethyl groups will be on the opposite side of on the neighbor's fence of the double bond. All right. All right. So another thing that's important to know here is a little bit of the terminology. In the past, the carbonyl group was the most important feature of the molecules, and scientists or alchemists were trying to label these carbons that were next to it. And so they say, okay, the carbon that is next to the carbonyl will be alpha, then the other will be beta, then gamma, delta, epsilon, and the last one will be the omega. All right? Now then came, nomenclature in a systematic way, and then they put a 1 here. So in the past, this was 1, this is 2, this is 3, and now we're like a little bit better. It's more structured. And then we say, okay, this is going to be carbons 1, this is going to be 2, this is going to be 3, and this will be 4. But even though we use that in nomenclature, we still refer to the carbon next to the carbonyl as alpha and the other one as beta. It's a really cool terminology that we use. And so the carbon will be alpha, and also the hydrogens will be alpha. So the alpha products here, atoms here, will be in red. The beta atoms will be in blue, and the gamma, in this case, will be in purple. Now, when you don't have the carbonyl, and you have, for example, an alkyl halide, the carbon holding the functionality, the carbon holding the bromine, in this case, will be your alpha carbon. And anything, notice that in blue here, we'll have 3 set of carbons that are beta, and the purple ones will be 1 more carbon away, so those will be your gamma. All right? So, so try to get used to this terminology. All right? All right. So, okay. So let me tell you something about elimination reactions. There's something called the Zaitsev rule. Zaitsev, as you can see, is a Russian name, and he came out with the idea of using his last name to predict the preferred compound in an elimination reaction. So with Zaitsev, you're looking for the most substituted carbon. And so Zaitsev is driven by thermodynamics, so the reaction will be done under heat conditions. And there's another alkene that's formed sometimes. It's called the Hofmann product. And this guy, as you can see, was a German scientist. Hey, I'm competing with the Russians, right? So now if this guy named his alkenes Zaitsev, I'm going to name my alkenes also under my last name. And he said, okay, I'm going to call them Hofmann. The Hofmann product is explained here. So for the Hofmann, you're looking for the least stable or the least substituted alkene. So, and you get it based on the conditions of the reaction. So we're going to talk about that in a minute. So let's go back to the Zaitsev. So in a reaction where you have eliminations, you always look for the different possibilities that you have. So if we were to subtract the protons here under path A in red, notice that I like to this is taken from this example is taken from a literature, but I have 4 carbons here, 1, 2, 3, 4. Basically, I'm dealing with that. This is 2-bromobutane that I'm dealing with, and I'm adding sodium ethoxide as the base. It's a small base, it's strong, so it's perfect for SN2 as well as E2s. And so we said that the E2 predominates over the SN2. Remember we said that last time? So in this case, it is the case. But you will always get when you do these reactions, when the E2 and the SN2 are competing, you get all the products of both. So notice that for the alkenes, the ones that are formed are 3. So notice that if we do the path in red, A, we're going to be deprotonating this hydrogen, right? Hold on, what's wrong here? Hold on, give me a second. This cable has always been like loose. Okay, and that's going to we're going to take this hydrogen, and this hydrogen needs to be anti-periplanar to this bromine right here, and so that gives us 20% of the least substituted alkene. So that's the Hofmann product, right? When we do path B, we take this hydrogen instead, and that hydrogen also has to be anti-periplanar to the bromine. We're going to kick off the bromine, and we're going to make 80% of the alkene with the double bond now in the middle. That alkene could be trans or could be cis. So that's something that you have to think. Okay, so if I'm making a double bond in the middle, I have 2 geometrical isomers. It could be it could be the E or the Z, or cis or trans. And so in total, you will make here, for this reaction, you will make 3 products, maybe 4. You make the SN2 reaction. But notice that this is a secondary alkyl halide. Secondary alkyl halide most likely will not form the SN2. The SN2 is mostly formed with primary benzylics and allylic halides. When we do the generalization of the halides, we put that those 3 are better than secondary, better than tertiary. But in reality, secondary will almost never be useful, and tertiary, the reaction will never undergo SN2 with the tertiary. You know what I'm saying? So the secondary is in between, and most likely will give you the E2 product. All right. So over here I have this slide where it says, okay, tetra substituted is most stable, tri substituted is the second most stable. Then you have the di substituted. I call this one here on the left as scissors, because I don't know what to call that alkene, but it looks like scissors, pair of scissors to me, where the 2 R groups are on the same carbon. Then you have trans. I was surprised that scissors was more stable than trans, and I looked it up in the literature, and yeah, it's more stable. And I would have thought that trans was, because it's more spread out. Yeah, less steric. With cis we have sterics, and you can see it in with this symbol here that means sterics in green. So these are the di-substituted, and then you have, of course, the mono-substituted, only have 1 R group. All right, so let's talk about the Hofmann rule. So in the Hofmann, notice that in the Hofmann, you will always have 2 products. You will have the Hofmann product, and you will have the Zaitsev product. For this particular case, if you deprotonate any hydrogen in blue on the CH3s, here or here, you get the same result, because those 2 methyls are equivalent. And so when I see something like this in using condensed structures, I transfer that to a linear structure. I like using linear structures. So this path A, the protonating there, will give me the Hofmann product. And if I do path B here, that will give me the Zaitsev product. Notice that Hofmann now is the predominant because of the conditions. Here are the conditions for Hofmann. You want a strong, bulky base, something like sodium tetroxide, no, sodium trimethoxide. Okay. Oh, no. This is called sodium t-butoxide. My bad. Sodium t-butoxide. And so you can use that. You can use LDA, HMP, HMPA, all those big bases that we're gonna mention them in the practice homework. And so you need something bulky. So as you can see, if there's something bulky here, if there's a bulky base, that's going to prefer to deprotonate the least hindered hydrogen, meaning that is the kinetic product. The most hindered or the most substituted product will give you the thermodynamically favored alkene. So because your base is so bulky, it's harder for it to deprotonate here, so it's easier for it to deprotonate right there. All right? And so the Hofmann is preferred. All right? So that's how Hofmann came out to life. Now, let's compare now the elimination one, the E1 versus the SN1. And I said last time that the SN1 will always beat the E1, except for two cases. The two cases is like when you're dealing with alcohols and you have a strong dehydrating acid like sulfuric or phosphoric acid, the E1 will win. I have a couple examples here for you guys. For the E1, in the E1, the reaction, the rate of the reaction is equal to the K constants times the concentration of the electrophile, because again, in the E1, you are depending upon the formation of the electrophile or the carbocation. Same thing. All right. But notice that the SN1 prefers the SN1 product is favored in 80%, and in this case, and the E1 here is only done on 20% yield. So this slide just tells you, okay, SN1 will be the E1. And so here is the mechanism for the E1. So again, the base will come and grab the H in anti-periplanar configuration. Again, this base will come like this. Hold on. And grab the H. Notice that the chlorine, this chlorine, is 180 degrees from the hydrogen, and that kicks that one off. So I have an example here. Say, for example, I give you this reaction, and I have a question for you. Which hydrogen is taken by the base when it attacks it, when it grabs it, to kick off the chlorine? The one that is wedged or the one that is dashed? The wedge one, exactly right. It's opposite. This is opposite to the chlorine. If you know that, you're going to be in good shape for the next milestone. That's going to produce this alkene. This H that is left here is this H right there. And of course, you have another H here that I'm not writing it. But yeah, that will be this guy right here. But I'm going to delete that so that it's not so crowded. All right. So I can even delete this one now. Now you know where it is. All right. So that's what that is. This slide here just talks about effects on the temperature. When you increase the temperature, you're going to increase the thermodynamically favored alkene. Nonetheless, the SN1 still will be the E1. All right. So here are the conditions that favor the SN1. So low temperature, weak base as nucleophile, tertiary carbon polar protic solvent. For the E1 to increase, you want higher temperature, stronger base as nucleophile, which is going to be a small base, and tertiary carbon polar protic solvent. In general, the SN1 reactions are not used because they produce too many products. It's only good to like study them. It's not good for synthesis. All right. So yeah. All right. So here is an example of an E1 competing with an SN1. Notice that the SN1 will beat it at 60% versus 8% the Huffman and 32% of the size F. During the E1 or the SN1, the main feature is the carbocation formation, right? That is your rate determining step. So if you have carbocations, this is what makes it hard. Look for carbocation rearrangements. So if you make a secondary and if the carbocation can rearrange to a tertiary by either a hydride shift or an alkyl shift, it will do it. It has time. And it will produce another bump in the energy diagram, but it's okay. Yeah, so that's what is happening. Let me see if we have, yeah, so there's no carbocation rearrangement there, but let's go to the next slide. This next slide is just talks about the previous slide. So generally speaking, we said the SN1 predominates versus the E1 except for dehydration of alcohols. And we're going to talk about that next. All right. So the dehydration of alcohols is when the E1 beats the SN1. Is the only time. And so when you have a strong dehydrating acid like sulfuric or phosphoric acid, they're going to dehydrate. So I call them the thirsty acids. This is my way of nicknaming them because sulfuric acid, when it's pure, is like 99.99%. It has the smallest amount of water, and so is phosphoric. So in the presence of water, they're going to grab that water because they can attract that to get a little more dilute. And so, let's see. So in the dehydration, look for the formation of the Zaitsev and the Huffman products, and look for geometrical isomers on the alkenes, if possible, for the Zaitsev. All right, the Huffman most likely is not going to give you, the Huffman is not going to give you geometrical isomer. It's going to put the double bond, usually like in the at the less hindered carbons, so the terminal ones. But the Zaitsev will, so you can have cis or trans or E and C like that. So notice here that for the Huffman, on the first example, we have 2 ports that are beta carbons, and those could interact with the sulfuric acid to form the Huffman product. Statistically speaking, yeah, okay, good. I mean, you could tell, okay, if the conditions were right, the Huffman would have been the better one, but the conditions are for Zaitsev. So it doesn't matter if statistically you have 2 ways to grab those H's to form the Huffman. But if you were to have like a bulky base, low temperature, then that will favor the Huffman. And statistically speaking, it will even favor more because you have 2 ways of making it. All right? But it's not the case here. The case is that this reaction, when it's heated, is driven thermodynamically. And so the Zaitsev will be the major product. So if we deprotonate here, that will give you, that will put a double bond here, and that will create the Zaitsev product. On the next example, when we deprotonate here, and this group is gone as a plus, and before you think about this OH has to leave in the form of water, like that, and it's gonna leave a plus right there. Then the elimination will take place. And so if you grab this H right here, that's going to make decisive, and you can do decisive, and it's going to give you the trans. That's going to make that trans. Also, if this bond rotates before it gets the hydrogen gets eliminated, that will give you the cis. That's why you have the possibility of making both cis and trans. And also the Hofmann in the second example, but the Hofmann will be only 20%. So you get 80% yield combined between cis and trans, and 20% yield for the Hofmann. So decisive rules here. So here what I say was you'll get 3 products based on the availability of hydrogens you have here. You get 3 products, 1 Hofmann and 2 decisives. And in the first example, which is also driven thermodynamically, you get 2 products. You get 1 Hofmann and 1 decisive. All right. Let's see what else I have here. Yep, so this is the mechanism for the dehydration of alcohols. The OH grabs the H from the alcohol, makes the water molecule, and now you have a good leaving group. That leaving group just leaves, and now you form a carbocation intermediate. Super cool. This guy is already tertiary, so it doesn't want to rearrange. But if it was secondary and it could become tertiary, it will do it. All right. And so, yeah, so after that, this intermediate is right here. Then with the conjugate base of the sulfuric acid, the HSO4 minus, you can do the different 2 approaches. If you did the protonate, here in purple, that makes this group makes that is the Hofmann. That is the same thing as, so you make the Hofmann there, and if you do that in the orange pathway, that makes decisive. All right. So this light here shows you that for the dehydration of alcohols, you're going to make the Hofmann. Here is the Hofmann, decisive, and sometimes the books ask you, and the SN1. The SN1 is not gonna be formed, I'll tell you that. But the literature wants to like trick you to see if you know this or not. This guy is not gonna be formed. But between the decisive and the Hofmann, because you have heat, that's going to favor my boy decisive. All right. All right. So if you haven't seen it yet, you should watch on Netflix. There's a movie called Enemy at the Gates. It's the story about Vasily Zaitsev, which was the best sharpshooter during World War II. It's super cool. You should watch it. It's awesome. All right. Enemy at the Gates. All right. So for the dehydration of alcohols, look out for carbocation rearrangements. I make that really clear because on my milestone, I can give you this reaction and give you options A, B, and C. And you have to know that the preferred product form there will be 2. Why is that? So think about it. The OH grabs the H from the sulfuric acid. That makes a water molecule that leaves. That puts a plus right here. That plus is rearranged because now at this point it's secondary. This is secondary carbocation. But this methyl group jumps. and then it puts the plus right there. And so you have, actually I have it right here. So that's the first step. The second step, make the tertiary carbocation, and then you can do the elimination. And so the SO4 minus grab the H, this H, and turns it into the favor. That's your favorite alkene. Tetra substituted, quite stable, and it's size F. All right, so you look at, how do I know that alkene is the most stable? Well, the more R groups makes it more stable. So this one will have 1, 2, 3, 4 groups. A, M, C are both Huffman products. You see that? But they're different. A happened from this reaction of your first carbocation. That's a question I could ask you. What is the precursor of A? And then you have to say, okay, it's this structure right here.
So theoretically, it can be formed if it doesn't rewrite.
Yeah, it can be formed. And so even if it's 5%, it will form. Exactly right.
So those three products are valid still.
Yeah, all these three products are valid and they're real. And this was from an actual experimental example. Now, 2 comes from the final product and the most preferred elimination product. And 3 also comes from the tertiary carbocation. You see that? It's deprotonating one of these. If you deprotonate one of those hydrogens, that makes C. All right? All right. Okay, so check this out. What if I didn't show you this? But yeah, now you know the answer, but I don't mind. What is the answer? What is the preferred product, the major product for this reaction? And I will give you 4 different examples. And the answer is 1, because for 1, this came about from a tertiary carbocation, and it's the most substituted. All right. So, okay. So let's figure that one out. I drew that here. So the first step is that the OH grabs the H from the sulfuric acid, makes a water molecule that leaves. This water plus will leave. When it leaves, it takes both electrons from here. And so it leaves a plus sign right there on that carbon. That's a secondary carbocation. Then it does 1 hydride shift. That makes a secondary carbocation still. And then when it jumps a second time, it gives you a tertiary carbocation. Kind of hard to concentrate with that noise. Yeah. All right, so we have 3 reaction intermediates before we get to the final product. You see that? That's why you need to figure it out. That's why you need to think. All right. So the stability of this will be, let's not do stability yet. So the tertiary carbocation, if it loses one of these hydrogens, it will give you 1. The secondary carbocation, this one, can give you 2 and 3, right? And this secondary carbocation can also give you 3. Number 4, this guy right here, comes from the protonation of one of these hydrogens. You see that? That forms the Huffman product. So here we had 2 Huffmans and 2 Sysefs. So the stability order will be first, followed by second, because it's Zaitsev, followed by 4 because it's Hoffman, followed by 2 because it's Hoffman. You see what I'm saying? Notice that I cannot choose 4 versus 3 because they came from different rearrangements and they came from different conditions. All right. If I was dealing with Hoffman conditions, then 4 will be favor versus 3. You see what I'm saying? Because those are die substituted. This is what makes this a little bit hard to come up with the answers. But you have to think what you're doing. Right now you are under Zaitsev conditions. Zaitsev. So the Zaitsev are preferred over the Hoffmans. All right? All right. I'm almost done there, guys, so hold on for a second. Then I can give you a mechanism in just a few structures. Look at this. It says correctly order the intermediate and final product. And this is all in my recording, so I'm just trying to walk you through that in case you haven't seen it. But step one is the OH gets protonated, right? So number 4 is made first. That's the first one that's made. You see that, right? It's this step right there. The next step is the living group. Kind of sounds redundant, but that's the only way I can teach it. And that will form number 2. You see that? So that will form number 2 is this guy right there. Then, can that rearrange? Absolutely yes, it can rearrange. So then that will make what? 5. This is your carbocation rearrangement. Where where's that? Where's 2? Yeah, right here. Where this methyl is gonna jump there and make a 1,2 methyl or alkyl shift. All right, and then after that, after 5 rearranges, this H is taken and it forms 1. All right, check this out. Structure number 6 came from 2. You see that? Here's structure 2. If you deprotonate one of these H's, that makes 2. That makes 6. And structure 3 came from 5. So you deprotonated one of these hydrogens. And those are Hoffman products. All right, so that will make 3. So 3 came from
Hoffman conditions is the only for the Hoffman conditions is the only time you're gonna have that double bond out there at the end.
Exactly right. These products 3 and 6, you should ignore them if you unless it's colder. Exactly right. If you see these reaction conditions here, those will be decoys. Those guys will be just useless. Yeah, right? But 4, 2, 5, and 1 are part of the problem. All right. So the last slide just tells you that always when you see the formation of a carbocation and the ability to form a geometrical isomer alkene, think about E and Z or trans and cis. All right. So that's what I'm saying here. So basically, in recapping here, yeah, whenever you have elimination, think of a Hoffman and think of a possible 2 Zaitsevs because you can have cis or trans. All right, so the total amount of product is usually 3. All right, if there's no rearrangement. If there's rearrangement, there's more. All right, so let's see something here before I go. I want to show you this important handout. I'm going to upload it on Canvas, and it's this one: comparison of the SN1, SN2, E1, and E2. And here I try to generalize all the reactions. So use this as a guide. The only thing that you have to take as a grain of salt are the secondary ones here. For the structure of the electrophile for SN2 and SN1. We put secondary and tertiary for the SN2, but those two never happens, right? They don't, we're just generalizing the statement. For the SN1, we do the same thing. We say secondary and primary for the SN1, but those two will never form the SN1 problem. The ones that you have to be vigilant is the benzylic, allylic, methyl, and primary for the SN2, and the benzylic tertiary, benzylic, and allylic for the SN1. All right, and so this I did in class, so I try to come up with this and teach it while I'm on the run. But here I made it really nice for you guys so you can study and analyze this and use it as a GPS for your responses. All right, I have 6 minutes. That's exactly the same time I had in the morning to start. Just a few examples here. All right, thank you for your patience. And now let's do the practice homework. Question number 1, it says describe the following chemical reaction as SN1, SN2, E1, and E2. Draw a curved arrow mechanism for each reaction. All right, so here I have potassium cyanide. This thing is a poison. This is what the Germans use as capsules to kill themselves, and they had a little pill that they will. A dentist will put the capsule in their teeth, and so when they're being interrogated by allies, they just crack that pill, and then with the saliva, it will form hydrogen cyanide, and that is a poison. It's gonna kill them instantaneously. And so, yeah, a little bit of World War II for you guys. So here we have a pure SN2, and it has really good conditions because you have a polar aprotic solvent, DMSO. All right, make sure you know the structure of DMSO. It's on the notes. So the potassium is a spectator ion. The cyanide has the negative, or the nitrile group has the negative charge. That's going to attack. It's going to do a backside attack and kick off the chlorine. This is a primary alkyl halide, perfect for SN2. This reaction is definitely an SN2 reaction. All right, we got 5 minutes. Oh, we can do more stuff. All right, notice that we have this on the next one. We have sodium hydroxide. Sodium hydroxide is a small, strong base. The sodium is a spectator ion. I don't care about that. I just care about the O- here. And the hydroxide has the coolest initials there in chemistry. No, I'm just kidding. So you know that O is really strong. It's gonna go and try to do a backside or an elimination. So in this case, it's doing an elimination. So because I'm gonna go around and grab one of these. And that's going to be the one that is anti-periplanar to the bromine. In this case, doesn't matter. It's achiral. This gets kicked out, and you form an E2. This is a pure E2. Notice that this is a polar protic solvent. It doesn't matter. Yeah, it doesn't matter because the E2 beats the SN2, and this was also a primary alkyl halide. All right.
Also, the heat doesn't matter because there's no other. It can't rearrange.
It cannot rearrange, exactly. The heat doesn't really matter here. It just makes the alkene form, and yeah, and that's the only place where you can deprotonate. All right. Notice that the the E2. We don't have carbocation rearrangement. This is a 1-2 punch that happens simultaneously. You grab the H, you form the double bond, you kick the bromine, all happening just like a conductor in a symphony orchestra, is doing it. So it's really fast. All right, the next example is interesting. What do you think you have there? SN1, very good. This is solvolysis because the OH came from the water, the most coolest molecule on the earth. I mean, it had to be, right? It's delicious. It's just simple, clear, doesn't have smell or flavors. Awesome. I mean, God made simple things. The simple things in life are the best, This bromine is that rebellious kid that wants to leave home at 18. I remember I left home when I was 20, and I never came back, only to visit. Honestly, I just came back home to visit my parents for like really short amounts of time. Once you taste freedom, man, you want to be by yourself. Right? So this is what happens. So this bromine wants to leave. This is Ben right here. BR. It's kind of like Ben, right? Ben, you already left the nest. So he leaves, and then that leaves a plus right there. And that plus sign with a neutral solvent. Notice that this is a neutral polar protic, and it's neutral, no charge. That produces the SN1. So this will go and attack there, and the Br takes one H and the protonates, forms the OH. Yes, sir.
So from SN1, we form a racemic mixture, so wouldn't you have the enantiomer also?
Oh, yes.
So you'll have the...
Yeah, but this is not chiral, but this group is the same as that. The wedge and dash is like a optical illusion. I hate it when that happens. But you're right, Ben. If you had something like a chloro or a methyl group, like right here, then what we'll do is we'll do a wiggly. Let's put a wiggly bond. That's usually used in literature too. When you do wiggly, you're taking care of both, or you do that one plus this. I should have done this example. And now this will be down, and this one will be up. And what will be the percentages? 50-50. Very good. Let's do like that. Let's keep it like that. It looks better. And actually, let's make this chiral now. This chirality transfers, and it stays because we don't touch it. You see that? It's super cool. All right. I think I'm going to stop there, and we'll continue on Friday. Now, we're going to go full blast on this thing. Have a wonderful day, guys.